Carlos, are you there?
Hello, hello. How are you?
Excellent.
Second,
Oh.
I close some windows. Yeah. Can you hear me?
Now I can hear you. Very good.
Can you see me?
I'll just say hello to the audience, and then you can go.
Give me a second that I open close some windows and open the file.
Yes.
And share my screen just to see.
So welcome to the afternoon session. We will have a talk by Carlos Nunez.
Can you see my
Duality. So what do we say? 25 plus questions? Yeah. So yeah. Keep it to 25, Carlos.
Yeah.
I'll warn you when it comes close. Okay, feel free to start.
Can you see my full screen now? Is the screen visible? Martin, is the screen visible? Hello? Hello?
We can hear you.
You can hear?
It's fine. You can just go.
Good. All right. So as you can see by the title, the talk is about ADS-CFT. I'll discuss work in that area. I will focus mostly on general ideas, right? In favor of all the technical details that will not be present in this talk. As Martin asked, I'll keep this talk to 20 minutes. So people, if wished, they can stop in the middle for questions. So the main idea will be to discuss the mapping between conformal field theories and string backgrounds in diverse situations. And in this case, I mean in dimensions 3, 4, and 5, okay? The final goal of all this line of research would be to calculate correlation functions in conformal field theories in different dimensions, in the deformation of the conformal field theories and along the normalization group flows. So as I was mentioning today, I will focus on 3 examples. The examples are going to be the first one, n equals 2 conformal theories in 4 dimensions, as there we all share a common language. N equals 4 conformal theories in 3 dimensions, and n equals 2 conformal theories in 5 dimensions. I will make some comments about RG flows away from the conformal theories, and all the lessons that I will discuss today are all generic, though I will discuss them in particular examples, they are generic. The talk of today is based on works to appear, works with Mohammad Akon and Andrea Legramandi that appeared yesterday, and one work with Andrea Legramandi that will appear a couple of weeks from now, and one we wrote with Andrea again in April of this year. But all what I will discuss is quite influenced by works I did in the last few years with a set of co-authors, faculty, postdocs, and students, and their names are listed here. So let me go for it. Let me first tell you a generic lesson here. The generic problem is to discuss a classification of a family of solutions in type 2 or M theory, and this problem is motivated by the problem of writing holographic duals to field theories. The field theories in this particular case are going to be conformal, they are going to be supersymmetric, and they will be half BPS, so they will preserve 8 Poincaré supersymmetries. And this problem can be tackled in dimensions 1, 2, 3, 4, 5, and 6, right? After that, there are no more conformal and supersymmetric theories. All these field theories will have at least one SU2R symmetry. This will have an important impact on the dual geometry, and they can also have other flavor-like symmetries. And all these field theories I will be discussing are usually realized on Hanani-Witten setups that contain DP, DP plus 2, and Neve-Schwarz branes. I will discuss this in examples, but just for you to fix ideas, in the case P equal 4, that corresponds to 4-dimensional conformal theories, there are going to be D4 branes in between Neve-Schwarz branes, that are these vertical lines, and D6 branes. And this will be associated with quiver field theories that will be on a line. They are called linear quiver field theories with gauge groups SUN1, SUN2, etc., and flavor groups. Okay, so this is the generic picture. Let me discuss a general picture of what happens in different dimensions. Here you see for each dimension people who studied the field theory, people who studied what's the Hanani-Witten setup on which the field theory is realized, and people who made lots of contributions to the holographic description of these problems in these different dimensions. So I will start with the 4-dimensional case, then move to the 3-dimensional case, and then move to the 5-dimensional case with less and less level of detail, because as you will see, everything is quite parallel. All the idea, once you get the idea, it works the same in all dimensions. The case of 2 and 1 dimensions was discussed on Monday by Yolanda Lozano. In any case, the generic thing here is that all these field theories will be conformal, they will preserve 8-point Carré supersymmetries, and they will have at least one SU2R symmetry. This is forced upon you by the supersymmetric and conformal algebra. So all the holographic dual backgrounds will contain an ADS space to take care of the conformality, a 2-sphere to take care of the SU2R symmetry, and some internal space, depending on coordinates that here I'm denoted with Y. There will be warp factors here and there, and the warp factors can only depend on these coordinates, and there will be also Neves-Schwarz and Ramond fields respecting these isometries that can only depend on those coordinates. Okay, so what generically happens is the following. In general, one proposes backgrounds of this type here in different dimensions, and one writes the BPS equations. The BPS equations are partial, because they will depend on these coordinates, partial first order, nonlinear, and coupled differential equations. So in principle, it's a quite complicated problem to tackle. But it happens in all these examples in different dimensions that doing algebraic manipulations with the BPS equations, you can write all those warp factors and other functions appearing in terms of a single function. I will refer to it as potential function. And what's interesting about this single function is that it satisfies a linear second-order partial differential equation. This partial differential equation, this Laplace-like equation, will need of boundary conditions, and it's in this boundary condition, these initial conditions, that the information of the conformal field theory will enter, and the good behavior of the background will be encoded. So the idea, the picture to keep in your mind is that you will propose backgrounds, you will write BPS equations, they will be quite complicated, but operating with them, you reduce everything to the resolution of one linear differential equation. And from that, once you solve it, you come back to these functions and then you write the background. So let me discuss this first in the case of 4-dimensional n=2 conformal theories. Okay, so the theories we will have in mind are linear quiver field theories with gauge groups SUN1, SUN2, up to SUNP, and flavor groups SUF1, SUF2, etc. The theories we will have in mind are realized on Hanani-Witten setups of this type, and the global symmetries of these field theories, particularly when they are conformal, the bosonic part of these global symmetries are SO2,4, that's the conformal group, and this is the R-symmetry of 4-dimensional n=2 theories, SU2 cross U1. The holographic background will contain, to represent these global symmetries, the ADS5 space, so the ADS5 isometries, the 2-sphere to take care of the SU2, and the S1 to take care of the U1, and the ADS5 to take care of the conformal group. As you probably remember, these field theories are conformal whenever a tuning between the number of colors and the number of flavors is satisfied. So basically, the beta function that in this theories is one loop and exact is proportional to twice NC minus NF. And this implies, for example, for this particular group, that 2N1 has to be F1 plus N2, this equality here. 2N2 has to be N1 plus N3 plus F2, this one there, etc. Okay. So I guess all of you are probably quite familiar with this, and all this information about the field theory can be encoded in a function. There are many other things that field theoretically one can learn, but this kinematic information can be encoded in a function that looks like this. It's a function that at x equals 1, it goes from 0 to p plus 1, as you can see here, is a linear by pieces, piecewise continuous. So the slopes go changing. And you can see that at 1 is n1, at 2 is n2, at 3 is n3, etc. At p is np, and at p plus 1 is 0. So something like what I'm drawing there. That's the derivative of the function, and the second derivative of the function at the jumps contains delta functions. And as you can see, the numbers that appear as coefficients of the deltas, this number or this number, etc., they precisely coincide with the number of flavors that are needed by conformality. So all I'm saying is that this is a way of encoding this kinematic data of the field theory. Okay, so let me see that there seems to be something on the chat. Okay, Kostas is telling something to Niels. So the problem of writing holographic duals to these field theories was first attacked by Lil, Nunez, and Maldacena, then taken back by Gaiotto and Maldacena to complete it. And the idea is that since these are n equals 2 theories, conformal, they will have to contain an ADS5 factor, a 2-sphere to take care of the SU2 R symmetry, and a circle to take care of the U1 R symmetry. These are the only consistent Ramon and Neves-Schwarz fields consistent with the isometries of the background. And as you can see, there are 2 coordinates, call it here eta and sigma, and all these functions, all these work factors from M1 to F8, they can only depend on sigma and eta. Okay, so you write the BPS equations for this. You process these BPS equations. They are complicated equations, but you process, you make algebraic manipulations with them, and you can write all these functions from F1 to F8 in terms of one single function and its derivatives. And here you have a sample of them, right? So this is how F1 looks, this is how F2 looks, etc. So what's interesting is that this B function solves a Laplace-like equation with certain boundary conditions. That's the Laplace equation. Those are boundary conditions. And the thing that acts as initial condition is this rank function I was referring to before, this R function containing the data of the quantum field theory. So this is a complete problem one can solve if one sits down, performs separation of variables. You will end up in a solution like this. It's a Fourier Bessel series after separating variables. And the coefficients of this Fourier Bessel series are basically the Fourier transform of this R function containing the data of the field theory. So algorithmically, the way you can think about this is the following. You think about the field theory that is conformal, that is n equals 2 conformal. These numbers have to satisfy certain relations. You write this rank function, and then you solve this Laplace problem. Once you have the function B, you come back here, write the functions from F1 to F8 in terms of B, and this background should know all perturbative and non-perturbative aspects of the field theory. With this background, one can calculate the associated page charges, and one calculates the number of Neves-Schwarz, the number of T6, and the number of T4s, and they coincide precisely with those needed in Hanani-Witten setups, like these ones for this particular field theory. Okay? So that's an immediate check. There are other checks involving linking numbers that can be computed holographically, and perhaps more interesting are checks involving central charge or entanglement entropy that can be very nicely written in terms of this R function and can be checked field theoretically. I'll have a word about this in minutes from now. Let me now discuss the case of 3-dimensional conformal field theories. Before going there, is there any question from the audience there or online? Let me stop for 10 seconds. And if there is any question, please unmute yourself.
There is one question.
Good. Let's continue. I will try to describe now how this story mirrors itself in the case of...
Carlos, there is one question.
Yeah, please.
Carlos, this is Dan. Sorry, I feel bad interrupting you.
Yeah, no problem.
Just silly. So the SU2, could that also be realized as left action on a 3-sphere instead?
Good. Actually, there are attempts like this, right? And probably that's how it will look when you lift the thing to M theory. There are attempts in realizing that SU2 not as a round to sphere, but say as a vibration, right, etc. That particular attempt was done by Oin, I think, and Bogdan Stefanski, and they fail they show that they fail in satisfying the n equals 2 conservation, right? But so in principle, this is what is known to work. What you are suggesting, I think, is what will happen if you lift this 2A situation to M theory. Okay. So the case of 4-dimensional n equals 4 conformal theory, 3-dimensional n equals 4 conformal theories, where the global symmetries are those of the conformal group and a couple of SU2s, and also preserving 8 supercharges, can be written following a very similar ideology. And the background that you write, and lots of people have worked on this. What I'm presenting here is the language we developed with Andrea Legramandi in a paper of some months ago. We write the background containing an ADS4, a 2-sphere, and another 2-sphere to take care of these 2 SU2s. And again, you see that there are 2 coordinates. I'm denoting them in the same way to make the point. These are the most generic configuration of Ramon and Neve-Schwarz fields. By the way, this is a paper with Andrea and Mohammed Akon, and this is the paper that appeared yesterday. The 5-dimensional case is the one I will discuss in a couple of transparencies. So once again, it happens that processing the BPS equations, all the work factors can be written in terms of a given potential function, solving a Laplace equation with certain boundary conditions. So you can translate this into a problem where you have 2 conducting planes at 0 potential, that's what I mean by this, and with a density of charge in between them. Again, by separation of variables, it's quite simple to see that this is the acceptable solution. And these coefficients here have the information about this function R, okay? Whatever that function R is. Then by quantization of the charges, the page charges present in the background, you find that that function R can only be, at least in this particular case, a linear by pieces function of this form. This is exactly the same form that I presented in the 4-dimensional case. And you can make an association between this R function and a Hanani-Witten setup, in this case consisting on Neve-Schwarz branes, D5 branes, and D3 branes. Okay, so the thing, as you can see, works very similarly in the 3-dimensional case, and in the 5-dimensional case, and this time again is work I did with Andrea in April. You propose a background containing an ADS6 that to take care of the 5D conformality, and a 2-sphere to take care of the SU2R symmetry. You impose 8 Poincare supersymmetries, and again, this is the most generic configuration of Ramon and Neve-Schwarz fields. Once again, all these functions, after processing the system of BPSs, can be written in terms of a potential. This potential satisfies a Laplace equation with boundary and initial conditions that once again can be put in correspondence with the same type of electrostatic problem containing 2 planes at a given distance and some density of charge. And again, this density of charge has to be a linear by pieces function, continuous, and you can make a very quick assignment between this rank function and a given quiver field theory. Okay, so there are various checks for these correspondences in different dimensions. Because of a matter of time, I will tell you only about one that is related to calculating what you may call the holographic central charge or the free energy of these particular field theories. This can be done for a given background containing an ADS and some internal space and some dilaton. The internal volume is defined as some weighted version of the volume of this internal space. As you can see, it's weighted by the dilaton and weighted by this prefactor. In any case, one calculates a well-defined quantity called holographic central charge, which has a meaning that we can discuss when you wish. And you can evaluate this holographic central charge in 3 dimensions, in 4 dimensions, and in 5 dimensions, doing the associated calculation for each of the backgrounds I was discussing. In the particular case, this can be done for any quiver, but in the particular case in which the quiver is this one, SUN, SU2N, SU3N, 4N, etc., up to SUP-1N with some flavors, the holographic central charge, the free energy, in 3 dimensions looks like this. In 4 dimensions, reads like this. In 5 dimensions, reads like that. And the factors like this logarithm here, or the presence of this zeta function in 3, are telling you that these results are purely non-perturbative. You will not get this by summing vectors and hypers, etc. So these are very non-perturbative results. And there are some matrix model calculations purely working with the field theory done by these colleagues here, where they basically check these results and generic results that one can get with supergravity using matrix model calculation. So there is a very nice match there. Let me discuss, just to go finishing, a couple of applications and a couple of predictions that this tell you, or that this picture gives you. You can discuss the case in which you take, say, for example, these 5-dimensional field theories that I was discussing a moment ago, and you compactify them on compact 2 manifolds or 3 manifolds or 4 manifolds. It's a prediction of this type of setups that at low energies you will encounter 3-dimensional or 2-dimensional or 1-dimensional correspondingly conformal field theories preserving supersymmetries. This is a non-trivial prediction of the holographic picture, right? And basically what you're doing is you are finding, let me move this a bit, you're finding a solution that asymptotes from ADS6 times a 2 sphere times this 2 space, and after the deformation and the compactification asymptotes into a lower dimensional ADS, some internal manifold, and the rest of the space. So if you look at the, if you look at the just one example for how this space-time look, well, they look like this. As you can see, the configurations are complicated. There are vibrations and all. But for particular values, solving the DPS equations of these functions f and h, the space goes, as I'm denoting here. Sorry, as I'm denoting. Oh, I cannot go back. I don't know for which reason. The space goes from ADS6. Let me see if I can move something and go back. Well, I seem to cannot go back. The space goes from ADS6 to ADS3 or ADS4 or ADS2. Okay. I had another application in the previous page to which I don't seem to be able to go back. Let me see if doing this will work. No. Let me just end these applications by saying that for the case of the 3D conformal theories that I discussed before, there is a very nice, very beautiful expression, holographic expression of mirror symmetry. And just to finish with this, in these classifications of backgrounds with different ADSs, etc., in the case of ADS2, ADS3, ADS5, or ADS7, it's possible, and I'm saying this because 2 toxin integrability follow, it's possible to find backgrounds on which the string sigma model is integrable. At least the bosonic part of the string sigma model admits a lax pair, okay? The cases of ADS4 and ADS6 that I discussed today with this language can probably be taken and understood. It's quite nice that in those cases, the integral background is unique and is always the deformation, an integral deformation of a solution known to be integral. So let me close with some conclusions. What I presented today for field theories in 4 dimensions, in 3 dimensions, and in 5 dimensions, repeat in the case of 1 dimension, 2 dimensions, and 6. The 1 and 2 dimensional case was discussed on Monday by Yolanda. These systems can all be thought in terms of DP, DP+2, and Neves-Schwarz branes. We studied RG flows away from these conformal theories, finding new superconformal theories. There is an interesting universality I didn't discuss today that shows you that some observables decouple the flow from the UV data, the CFT data. I did not discuss this today, but willing to say more. And it might be quite useful, and I'm saying this because people in the audience are quite proficient on this. It might be quite useful to unify all these different dimensions into one single taxonomy, right? To understand all these backgrounds and their deformations under one single language, and that might be possible. It will be quite interesting to study how integrability and other observables behave under RG flows, and it would be nice to extend these classifications to N=1 linear field theories. With this, I finish. Thanks very much. Let me see if I can, in some way.
Carlos, do we have any questions from the live audience? Not even a small one. So we check the distant audience. Anyone raising the hand?
Oops.
They don't. Okay. No.
Thanks very much.
You can ask a small question. You can ask a sort of medium-sized question if you like.
Yeah, please.
This is really, what were you thinking for the N=1 classification? Can you say something how that might go?
Yeah. You know, the attempting something similar for the N=1 case was done. There is a particular paper I like by Ibu Ba. And the main problem there is that after processing BPS equations and etc., he arrives to a differential equation, one single differential equation that is of the Monge and Peart type. So it's very non-linear and quite difficult to solve. So I think this thing of arriving into a Laplace equation is a bit of magic of 8 supersymmetries. And whenever you work with 4, at least in certain variables, you arrive at a more complicated equation to solve, right? So it's non-linear and with sources. So it's quite hard. But maybe there is another language in which the thing behaves easier, at least, okay? And I don't know which would be that language. What I'm sure is that people in the audience here know a lot of geometry so that to be able to write the problem in the most efficient fashion, right? And then probably it's a matter of changing variables. But of course, I don't know beyond those few papers in the bibliography.
Okay, let's thank Carlos again.
Very much. I'm not sharing anymore, right?
Move on. The next speaker is Ben Hoare. Ben, can you hear me? Can I hear you? Ben, are you there?
Oh, hi. I don't know. Can you hear me?
Yes. Yeah, okay. Yes, we hear you, Ben. And we also see you. Will you see
great.
them? Okay. I don't know the title of your talk.
Sorry, let me share my screen and then that will tell you. Sorry.
And we will see it. And 25 plus questions, and you're set to go.
That's great. Thank you very much. So thank you for the introduction. Thank you to the organizers for the invitation to speak. I would have absolutely loved to be in Corfu. Unfortunately, it was just not possible this time. Hopefully in the future. So what I would like to talk about today is some work that I've done and sort of ongoing as well into Yang-Baxter deformations of this model, the Principal Chiral Model plus Wess-Zumino term. I'll introduce all these different things as we go on. But these are examples of integral sigma models in 2 dimensions, and such models are kind of interest in for many reasons in theoretical physics. One of the kind of most interesting developments in the study of 2D integral sigma models over the last few years is that the landscape of these models continues to grow. More and more are discovered, kind of understood how these things are connected. And there's been a number of different approaches that have been employed to do this. So one is direct construction. This has been around a long time. It's very challenging. Another that's been around a while is this 2D Hamiltonian formulation, which kind of uses a doubled formulation. Nowadays, these go by the name of E-models. There's the affine Godin integral systems realization, higher dimensional semi-topological gauge theories. This includes things like the 4D Chern-Simons, and then more general guiding principles such as dualities and deformations. So all of these things, or the different approaches are intimately related, but they all provide different insights into this landscape. So I think the classification remains a really long-term aim, and in particular, one of my main motivations for this is to find new solvable string sigma models. What I want to talk about today is a certain corner of this space. So that's highlighted by this diagram. So we have the Principal Chiral Model, which is going to be our starting point. And then it's well known that you can either add a Wess-Zumino term to the Principal Chiral Model, and you still have an integrable sigma model, or you can consider a so-called Yang-Baxter deformation. And the question I want to look at is when you can combine these two into a Yang-Baxter deformation of the Principal Chiral Model plus the Wess-Zumino term. So let me just start with a bit more kind of motivation of why we might be interested in such a question. So the Principal Chiral Model is a 2D integrable sigma model. It has its target space is the Lie group with the bi-invariant metric. I've written the action here. I'll come back to that shortly. But the important point is that H, which is the sigma model coupling, is asymptotically free. It vanishes in the UV, and it's strongly coupled in the IR. And it's well known that this is at least a dynamical mass generation and non-perturbative mass gap, at least for compact Lie groups. And there's a very beautiful story describing the integrability of these models. So if we add a Wess-Zumino term, so this is this term here, what happens is the IR behavior is modified. So there's a fixed point now at H equals 1, which corresponds to the Wess-Zumino model, and the theory flows to this fixed point in the IR. So adding the Wess-Zumino term modifies the IR behavior. However, these Yang-Baxter deformations, they actually end up, what they do is they actually modify the UV behavior. So there are different types of Yang-Baxter deformation. They are labeled by a parameter c², which is a real number. And at least for when c is not equal to 0, the UV behavior is modified. When c is equal to 0, the RG flow is actually unchanged. So c² is real, so there are different cases. We can have c being imaginary, purely imaginary, non-zero. In this case, the RG flow ends up having this rather weird behavior. So here I have the PCM case on the left and the PCM plus Wess-Zumino term case on the right. the RG flow has this weird periodic nature, which leads to some unusual UV behavior. It's not really clear if these quantum theories are UV complete. However, these non-split, these deformations when C is imaginary, are important for these scale invariant, for constructing deformations of world-sheet sigma models in string theory. In this case, the relevant supergroups have vanishing Joule-Coxeter number, and this means that there's actually no RG flow. The models are scale invariant themselves, so this story doesn't apply. On the other hand, we can consider the case when C is real. And this case is particularly interesting because we end up with a new non-trivial fixed point in the UV, which is closely related to a gauge Wess-Zumino-Witter model. And we end up with integral models that for the PCM case, they become strongly coupled in the IR and they flow to this fixed point in the UV, or including the Wess-Zumino term, they flow between two different CFTs. And this leads to so-called ancient solutions of these RG equations. Unfortunately, at least for the models that I'm going to discuss today, because we're just considering the PCM, if we want a real action, this typically requires non-compact real forms. Nevertheless, these models are potentially of interest in the context of other areas of theoretical physics. The final class of these homogeneous deformations, and in this case, the deformation doesn't modify the RG flow of the model. And more or less, they correspond to twisting the symmetry algebra, and they still play an important role in understanding these integrable systems. So given all this nice structure, it's kind of interesting to see, can we actually construct Yang-Baxter deformations of the Principal Chiral Model plus Wess-Zumino term? And so these are the questions I'm going to try and answer in this talk. I'll mainly actually focus on the first one. I don't really have time to cover the second two. So for which Yang-Baxter deformations of the PCM can we also include a Wess-Zumino term? And there's a very nice algebraic story that underlies this, and it also fits in nicely with all these various general organizational frameworks that I mentioned at the beginning. So that's hopefully a motivation for why we're interested in this question. So the structure of the talk, you can probably already see from the top, but more or less that was the introduction. I'll spend a bit of time, I'll very briefly introduce the Principal Chiral Model and its Yang-Baxter deformation, just highlighting the key points about the model, and then I'll turn to this Principal Chiral Model plus Wess-Zumino term and its Yang-Baxter deformations. And then to finish, I'll end up with some concluding comments. So just to put everyone on the same page, I'm just going to very quickly recap the Principal Chiral Model. So the Principal Chiral Model for a simple Lie group G has this action. Here H is this inverse, is the sigma model coupling, it's the inverse radius squared. J plus and J minus are the pullbacks of the Mara-Cartan 1 form to the world sheet. We use light cone coordinates on the world sheet, which are defined in this way. And kappa here is just a normalized killing form. It's normalized such that it's positive definite for compact groups. So this is the action of the Principal Chiral Model. It has a global G times G symmetry, which acts in the obvious way. And the equations of motion can be written as the conservation equation for the right-acting symmetry. This is this conservation equation. K plus and K minus are defined in terms of J plus and J minus. They're just proportional. And I've included this weird 1 over psi times H. So here, psi is a free parameter, which just reflects that the fact that this conservation equation is linear. H is our sigma model coupling. So psi is just parameterizing a freedom in normalizing the current. And if psi is equal to 1 over H, then K plus minus is also flat. You may say at the moment, why are you bothering to introduce psi? This will come back later and will be relatively important. What I want to emphasize here is that we have on the equations of motion, we have a current that is both flat and is conserved. And whenever we have such a current, we can write down a lax connection for the model, takes the following form. So it's just proportional, the connection is just proportional to this conserved current weighted by this 1 minus plus z, where z is the spectral parameter. And as usual, the lax connection is flat for all values of the spectral parameter, if and only if the equations of motion are satisfied. So I won't go into these final 2 points in much detail, but one can go further and compute the Poisson bracket of the lax matrix with itself. It satisfies this non-ultralocal Maillet bracket. It's not particularly important what this is, but what it means is that one can construct the required infinite towers of conserved charges in involution that you need to really claim that you have an integral model. So that's the Principal Chiral model. Now let me turn to the Yang-Baxter deformation of the Principal Chiral model. So all that changes is that in between this J plus and J minus, I insert this operator here, 1 over h minus nu r g. So h is the sigma model coupling from before. Nu is just a real parameter, and it's the deformation parameter of the model. So when nu goes to 0, this term goes away, and we just end up back at the PCM. R is a constant linear operator. It maps from the Lie algebra to itself, and it should satisfy some properties. In particular, it should be an antisymmetric solution of the so-called modified classical Yang-Baxter equation. I'll write this on the next slide. And then Rg is just R conjugated by the adjoint action. This is slightly different to how you, if you are familiar with the Yang-Baxter deformation, this is slightly different to how you may normally see it written. I've written it in this form just because in this parameterization, this parameter nu does not run under the Rg flow, while h is the runs as I discussed in the introduction. So this operator R, which maps from the Lie algebra to itself, should satisfy these following two equations. This first line is the modified classical Yang-Baxter equation, and the second line is just the antisymmetry of R. C squared is this parameter that I was discussing in the introduction. C squared should be real, and that leads us to these following three cases: imaginary, real, and vanishing. C being imaginary, real, and vanishing. In general, though, we'll just keep C general and just treat all three cases at the same time. The only other piece of notation that I want to introduce is this bracket with the subscript R here. This is defined in the following way, and it will come back later in the talk. So it's known as the R bracket. So as I've constructed them or written them, these Yang-Baxter deformations have at least a global G symmetry, which acts from the right. Again, the equations of motion can be written as the conservation equation, which is just written here. Again, we introduce this free parameter psi. And now we find that if psi is equal to this combination of h and c and nu, then k is also flat on shell. And the Yang-Baxter deformations of the Principal Chiral model are integral, and the lax connection is just given, takes the same form as before. And again, the lax matrix satisfies a non-ultralocal Maillet bracket. So that's a bit of a lightning introduction to the PCM and its Yang-Baxter deformations. I now want to turn to the Principal Chiral model plus Wess-Zumino term and its Yang-Baxter deformations. Trying to follow a relatively similar strategy to what I was describing for the Principal Chiral model. So let me first start with the Principal Chiral model plus Wess-Zumino term. More or less, the first term here is just the Principal Chiral model, and the second term here is the usual Wess-Zumino term defined in 3 dimensions. And as ever, for the path integrable to be independent, to be well defined, this parameter k here should be integer valued. And related to this, k does not run under the Rg flow, only h runs. And there's a fixed point, which is h equals 1, which corresponds to the Wess-Zumino model, which this model flows to in the IR. And again, we can construct a conserved current corresponding to the right-acting G symmetry. And if we introduce this parameter psi, there is a choice of psi for which this conserved current is also flat on shell. And again, the model PCM plus Wess-Zumino term is also integrable. And this is its lax connection, which again satisfies this non-ultralocal Maillet bracket. So motivated by all these pieces that I've introduced, so the PCM and its Yang-Baxter deformation, and then this Principal Chiral Model plus Wess-Zumino term, what we want to explore is Yang-Baxter deformations of the Principal Chiral Model plus Wess-Zumino term. And to do this, I'm going to use the following strategy. So we're going to start by assuming that the the action has a right-acting G symmetry. So in particular, here, if O is just equal to 1 over H or K over H, then this is just the Principal Chiral Model plus Wess-Zumino term. And I'm just going to introduce a general operator O here, which is a constant linear operator mapping from the Lie algebra to itself. And then OG is again just this operator O dressed by the adjoint action of G. So we're going to assume that the lax connection takes the form written here. So again, we have K plus minus 1 over 1 minus plus Z, where K plus minus are the conserved currents for this right-acting G symmetry. And we've introduced again this parameter 1 over Xi. And of course, this is only a lax connection if this conserved current is also flat. So the question that we want to answer is, for which operators O is this conserved current also flat? And when we have such an operator O, then we know that we can construct a lax connection and we have an integrable model. So so let me start by parameterizing this operator O in terms of a new operator S. So S here is again constant linear operator mapping from G to G, and a free parameter H. So I'm going to parameterize O in this way, which may seem a bit perverse at first. The motivation is that you get nice equations coming out at the end. The role of introducing the free parameter H is essentially that it allows us to normalize S however we want. So by rescaling S, we can absorb that always into a redefinition of H. So under the assumptions from the previous slide, integrability for general parameters implies that S should satisfy these equations here. So these look remarkably similar to the equations that R should satisfy, but there are subtle differences. So in particular, this almost looks like the modified classical Yang-Baxter equation, except for this term sitting here, which is linear in S. And then instead of S being anti-symmetric as R was, now S turns out to be orthogonal. So SS transpose should be equal to the identity. So in order to understand or try to explore solutions of this set of equations, I'm going to focus on those operators S for which we can construct a smooth K to 0 limit. So as K goes to 0, we expect to recover the Yang-Baxter deformation of the Principal Chiral model. So in this case, this operator O inverse should equal H minus nu R. So this was the operator that appeared when we constructed the Yang-Baxter deformation of the PCM. And we're simply going to perturb around K equals 0 with some expansion parameter HK, which is much less than 1. So we're going to take O inverse to be equal to H minus nu R plus some small perturbation, and then require that the conserved current K plus minus is flat at this next subleading order. What we end up with is an overdetermined set of equations for O hat. So the first thing that we notice is that the symmetric part of O hat is proportional to the identity operator. So pretty much we can ignore it. And this follows from Schur's lemma. The equations for the antisymmetric part of O hats are more interesting, and they can actually be most conveniently written in terms of the Lie algebra cohomology of GR, which I haven't actually introduced yet, and which I'll do now. So what is this GR that I write here? So if you recall, back when I introduced these Yang-Baxter deformations, I briefly mentioned that there was this so-called R bracket, which is defined in the following way. And when R solves the modified classical Yang-Baxter equation, the R bracket actually satisfies the Jacobi identity. And actually what this means is that the R bracket defines a second Lie algebra on this vector space G, which we denote GR. And as ever, it follows that we can introduce the associated Lie algebra cohomology. This is just for the trivial representation of GR. And this is just the usual definitions for n cochains and so on and so forth. And as usual, we just have this and the exterior derivative. And as usual, we have that dr squared is equal to 0. This follows from the Jacobi identity. Good. So we can introduce the following 3 cochains. So omega x, y, z. So here x, y, and z are all elements of the Lie algebra. The first one is just kappa. This is the normal Lie bracket.
For interrupting. You have around 5 minutes. Is that okay?
Yeah, that's absolutely fine. Yeah.
Okay. Thank you.
We have these 3 cochains. So this first one is defined in the usual way, and there's a second one, which we denote omega r, is defined in terms of these operators r plus and minus, which are just equal to r plus and minus c. And both of these cochains, it's fairly easy to check. They are both closed. So what we find is if we denote the antisymmetric part of O hat by A, which I'm going to write, and I define this 2 cochain, which basically encodes A, then for a particular Yang-Baxter deformation of the Principal Chiral model to generalize to this Principal Chiral model plus Wess-Zumino term, we find this particular Lie algebra cohomology condition that essentially omega r plus some multiple of omega should be exact, should equal dr of psi a. So, okay, this is a nice condition, and we wanted to try and understand for what Lie algebras and what R matrices this thing is satisfied. We didn't manage to come up with a universal answer, but what we managed to do was scan a number of known R matrices, and we pretty much universally found that one of the following 2 things happens. So either omega R is equal to 0, in which case omega R plus alpha omega is equal to 0 for alpha is equal to 0. And this is an example for G equals SL3. Or the other thing that might happen is that omega R plus alpha omega is not exact for any alpha. And here is an example of that. So what we kind of naturally conjecture is that these are the only 2 things that can happen, at least for simple Lie groups, and that if omega R equals 0, then the Yang-Baxter deformation of the Principal Chiral model plus Wess-Zumino term exists, otherwise it does not. So there is a natural action that one can consider in this case. S is this operator S, which is here, or SG, is essentially equal to e to the row RG. So R, remember, is antisymmetric, so e to the row R is indeed orthogonal. And one can recover the various different models, the Principal Chiral model plus Wess-Zumino term, these Yang-Baxter deformations by taking various limits as you would expect. So again, this parameterization is particularly nice. K and rho do not flow under the RG flow, while H does flow. And there is again a fixed point at H equals 1, which corresponds to the Wess-Zumino model, Wess-Zumino-Witten model. And at this point, the dependence on the deformation parameter drops out. And so this model, this final slide is just to say that this model is indeed integrable. This operator O this operator S, which is equal to this e to the rho times r, solves this equation if and only if r solves the modified classical Yang-Baxter equation now and omega r is equal to 0. And then one can construct a normalized conserved current that is also flat, and therefore the model admits a lax connection, and this satisfies a non-ultralocal Mayer bracket. So just let me summarize these results briefly. So we started from the PCM, we considered both its Yang-Baxter deformation and the case where we add a Wess-Zumino term. And for a particular Yang-Baxter deformation of the Principal Chiral model to generalize to the including the Wess-Zumino term, it is necessary that we have this combination is exact for some alpha in R. And when omega r is equal to 0 itself, then we can construct an action for the model and prove its integrability. So there's strong evidence that omega r is equal to 0 is a necessary and sufficient condition as well. And it's an interesting question as to whether this can be rigorously proven. So the final thing I want to just discuss briefly is some possible generalizations. So some things that I didn't really have time to talk about. So the structure of these Yang-Baxter deformations of the Principal Chiral model plus Wess-Zumino term means that it can be formulated in terms of these various organizational frameworks that I mentioned in the introduction. And this is potentially useful for exploring various generalizations, some of which I list here. And it would also be interesting to see if we can find new models that interpolate between non-trivial CFTs in the UV and IR. There's been some interesting recent work in this direction over the last few months. And also, can we find new scale invariant models that can be used to build string sigma models? This would be very nice if this was possible. So that's everything I have to say. Thank you very much for listening. Thank you.
So are there any questions from the audience? Do we have any online questions? No. Okay. Then we thank you again, Ben, for a nice presentation. Thank you.
Thank you.
The next speaker is Konstantinos Zoubos.
All right. I'm trying to share my screen. I guess I need some. Okay, great.
We see you, and can you speak?
Okay. Can you hear me?
Very good. We can hear you, and we see your slides. Everything is fine. So, dynamical spin chains in N=2 superconformal gauge theories. So let's keep it to around 25 plus questions, and you're free to start. Welcome.
All right, thanks a lot. Let me also thank the organizers for the invitation to speak, and apologize for not being able to be there physically this time around. I've always enjoyed participating in these Corfu meetings. So I'm going to discuss today some work that appeared recently with Eli Pomoni, who I think many of you know, and with my PhD student here in Pretoria, Randall Rabbit. So this is a rough outline of what I want to say. I'll first very quickly review how the spin chain story arises in the planar limit of N=4 super Yang-Mills, and then I will discuss some analogous spin chains for the N=2 orbifolds of N=4, and more specifically, the marginal deformations of those orbifolds. Then I'll quickly show how one can use the coordinate Bethe ansatz to solve the 2-magnon problem in these orbifolds, the marginal deformed orbifolds. And then to end the talk, I'll give an interpretation of these spin chains as statistical, two-dimensional statistical models. So let me start by reminding you of the n=4 theory, where obviously the field content contains 6 scalar fields, as we all know, which I'm going to be referring to in superspace language as x, y, and z. So chiral fields. There are adjoint fields, and we'll be focusing, or what we want to understand, of course, is observables, such as gauge invariant operators, because it's a gauge theory. And since it's also a conformal field theory, we mostly care about 2- and 3-point functions, because the rest could be, in principle, constructed using the OPE expansion. For n=4, I'll be focusing just on the spectral problem in this talk. So the goal is to compute anomalous dimensions. And it turns out, to the restrictions of conformal invariance, this really 2-point functions, for instance, only end up depending on this dimension here, delta, which at tree level is just simply the length of the operator. So if the operator, I'm talking only about scalar fields, so they have canonical dimension 1. And if the length is L, then this is what the dimension is. But this, of course, gets corrections. And at one loop, there are different kind of diagrams that will give you corrections. And as is well known, Minahan and Zarebo showed about 20 years ago that this problem can be mapped to the problem of solving the Hamiltonian, or diagonalize the Hamiltonian of an XXX spin chain. So if we focus on the SU2 sector made up of just 2 of these scalar fields, you can map a field to spins down and up. And the Hamiltonian, so the action, the dilatation, the planar dilatation operator on these states can be mapped to the action of a ferromagnetic nearest neighbor periodic spin half XXX Heisenberg Hamiltonian. So the spectral problem is mapped to a Bethe-Ansatz solution, which of course exists for this kind of problem. Now, there's a lot to say about integrability, which I'm not going to be giving references at the moment. But if you combine these perturbative, there's a perturbative approach with the strong coupling and get important input from the string side, including spinning strings and the sigma model that we just also heard about a little bit, then together can provide lots of insight into solving the all loop problem. And a lot about it has been understood, in particular with a quantum spectral curve that is a very powerful way of understanding the spectrum. 3-point functions are also under study. I'm not going to have anything to say about that. But my interest is in reducing or moving away from the n=4 theory and looking at theories with less supersymmetry. There are many examples of that in the literature, like the ABJM theory. There's ADS3/CFT2 settings. There's also non-maximal supersymmetry. For instance, you can marginally deform the n=4 case. The general rule is that once you do that, integrability is broken. In this talk, I'll focus on a different kind of deformation, which is an n=2 superconformal deformation. And I will discuss, as I said, the spin chains and that appear there. So let me start by taking a Z2 orbifold of n=4. Okay, so we start with n=4. We have SU2 engaged group, and we do a projection in R symmetry space. You see I'm projecting X and Y to minus themselves. You can also see that there's a projection, of course, in the transverse space to the D3 branes that you use for this brane setup. And you also do a similar projection, you do a projection in color space by this matrix. And combined, these two give you these fields. So basically, they kill several components of the 2n by 2n fields and leave you with Z, which contains 2 adjoint fields, and X and Y, which contain 2 bifundamental fields each. The superpotential also gets expanded out in this particular way. Usually, we represent these theories with a quiver diagram, where the nodes are the gauge groups, and the arrows tell you which fields go between which nodes. So the adjoints go to the same node, the bifundamentals change nodes. Or you can use a bipartite graph, where now the face is the gauge group, and the fields are the edges between them. So you see the blue edge here corresponds to this blue adjoint field, for instance. This will come back a little bit later towards the end. This case of just taking the orbifold, not only for Z2, but for the Zn case, so more general cyclic orbifolds, has been studied by Bisond and Reuben, and it remains integrable. The Hamiltonian is still Heisenberg to one loop, and the only big difference is that you get twisted sectors. So you also have this element gamma that I had before. You can also include that as somehow an extra kind of magnon, which basically just modifies your boundary conditions. So that's the only thing that really changes if you orbifold the theory. And even if you go beyond one loop and to bigger sectors, you can still orbifold the Bethe-Hansens of n equals 4 and get an n equals 2. There's also a similar story for more general, for instance, non-abelian orbifolds, and things seem to work in exactly the same way. What we're going to do now is we're going to move away from the orbifold point. So we're going to take the two gauge couplings to be different. So at the orbifold point, of course, you start with a single gauge coupling of n equals 4, you orbifold that, and you get two gauge groups which have the same coupling. Now you deform away, and you get two different terms of the superpotential. This is a marginal deformation because it preserves n equals 2 supersymmetry and conformal invariance. And it was studied in detail in this paper, where their main interest was the fact that this theory interpolates between n equals 4, the n equals 2, I should say n equals 4 orbifolded, which is at G1 equals G2. It's still an n equals 2 theory. And the n equals 2 superconformal QCD, which occurs when you take one of the couplings to 0, in which case that gauge group becomes a global Flavel group. And then it's some superconformal QCD type theory. Here we don't have any flavors in the general case. But their conclusion was that the S matrix, after studying the spin chains that came out of this, the S matrix does not satisfy the YB, and thus the conclusion was this theory is not integrable in the general case. It was integrable, of course, in what I call the n equals 4 point, really the n equals 2 orbifold point, and and when G2 is 0, it also seems to be somehow integrable, but not in the middle. In this work, we're going to revisit this conclusion by trying to better understand the spin chains that arise in this interpolating theory with G1 and G2 arbitrary, and understand their algebraic structure. So we're going to look at two different SU2 sectors. One is the one made up of the X and Y fields, and the other one is a sector made up of the X and Z fields. Now, this used to be an SU2 sector in the n equals 4 theory, but obviously here, Z is a different representation of the gauge groups than X or Y. So this SU2 is broken. Okay. But we're going to see that there are some interesting things to say about this SU2. So we can look at the various diagrams that contribute to the Hamiltonian. And you can see that some of them depend on G1, some of them depend on G2. So depending on which node of the gauge group is involved, time moves upwards in these pictures. And we can write the Hamiltonian, where this is still an SU2 sector, but now, of course, we have 4 fields. But you notice that our basis is not 16-dimensional, as you might expect. It's only 8-dimensional because there are some contractions you cannot do. Because the fundamentals, these are all by fundamentals, and you cannot, for instance, contract 1, 2 with 1, 2. The gauge indices don't match. What's interesting here is that this has a block diagonal form, and the block depends on whether the gauge group to the left is gauge group 1 or it's gauge group 2. So we will prefer, instead of using this kind of truncated basis, we would actually prefer to use what we're going to call a dynamical. This is to be explained what dynamical means. A picture where I talk about each block Hamiltonian on its own, acting on the original n equals 4 fields, but now there's going to be some extra information which is going to tell me which is the gauge group that appears to the left here. And that's where the dynamical is going to come in. For the XZ sector, things are kind of similar. You also can calculate all the contributions to Hamiltonian, and you get a different kind of Hamiltonian, which in this dynamical picture looks like so. So again, there's 2 Hamiltonians depending on whether the gauge group to the left of the fields is the first or the second gauge group. And you can see they're kind of inverses of each other. What we get out of this is that if you look at this XY chain, so this is the sector with both by fundamentals, the chain is strictly alternating. So you get this H2, I indicate by red the second gauge group, by blue the first gauge group, and each Hamiltonian looks at what the gauge group is to its left of the site it acts on. And so then you use H1 if the gauge group is 1, you use H2 if the gauge group H2. But you see this always alternates because these are by fundamentals. So the gauge group just alternates between each node. The XZ chain is a bit different. It's actually dynamical in the sense that the Hamiltonian depends on how many X's you've crossed, but does not depend on how many Z's you cross, because Z is an adjoint field, and crossing a Z field does not change the node of your quiver. So things are a little bit more complicated in this Hamiltonian, and it's convenient to introduce what you call a dynamical parameter, which I've done here. I'm calling H1 and H2, I'm calling them H lambda and H lambda prime. The idea being that there's going to be a parameter which tracks which gauge group is to the left of each site. And this parameter changes when you cross XY, but does not change when you cross a Z field. Good, so that was the description of the Hamiltonians. Now this is the setup we're going to be looking at, and I'm going to be focusing, just for lack of time, on this XY chain and just quickly explain what the Bethe ansatz looks like for a chain like this. And then I will continue with some statistical mechanics interpretation of these models. So of course you can diagonalize the Hamiltonian and use kappa equals 1. So this is the parameter kappa, which is barely visible here. Kappa equals 1 is the orbifold point. This is just an XXX model. And in the untwisted sector, just pure XXX for, say, length 6. And you see that the eigenvalues change as you move away from kappa equals 1. And our goal is going to be to reproduce this from a Bethe ansatz. Now, to give away the punchline, we are going to manage to reproduce the blue lines, so the 2 magnons and the 1 magnons. We are still working on the 3 magnon problem, and that, of course, is related to the question of integrability, which I'm going to talk about when I get there. Okay, so to remind you how it works for the standard XXX case, to solve the 1 magnon problem, you make a plane wave ansatz like so, and you find that this is a solution if you have this very simple dispersion relation. So if the energy is related to the momentum that you put here by this simple formula. In our case, because it's an alternating chain, so the Hamiltonian at even and odd sides is different, you need to take that into account by including even and odd coefficients here. And it turns out that you need a specific ratio of these coefficients for this to be a solution. And on top of that, you need this kind of dispersion relation. Now, this dispersion relation is very well known, or these types of dispersion relations are very well known in what is known as staggered models. And many studies of phonons and stuff use these kinds of, or end up with these dispersion relations. The main difference from the undeformed case, so kappa equals 1 here would be this, so the cosine relation, that's this solid line. But the moment you deform away from kappa equals 1, you obtain a gap. So scattering states are not allowed to be in this gap because so real momenta, if you have a state with a real momentum, it cannot end up being in this gap. And there are 2 kinds of branches. The lower one is traditionally called the acoustic branch, and the upper one is called the optical branch. So that's what we find. And one thing that I should mention, but I will not mention it again until the conclusions, is that if you want to uniformize this, which means to find a rapidity variable, it naturally introduces elliptic functions. While this case, if you uniformize this, it's a rational model. So you can just get away with just polynomial functions in the rapidity. So here you need elliptic functions. To look at the 2 magnon case, things are normally, the normal 2 magnon case is dealt with by splitting your equations into non-interacting equations, where you see the magnons, these are 2 Y magnons, but they're separated. They're not touching each other. And the interacting equations where they actually touch. And the way you proceed, and this is according to the Bethe original ideas, is you solve the non-interacting equations first. And you do it using a plane wave type ansatz. And then you impose the interacting equations, which fix the relative coefficients. So this AP2 over AP1 is fixed to be the S matrix of the theory. Our case is more complicated. And we followed old work of Medved, Southern, and Levis in understanding how to work in our case. The problem is that because our dispersion relation is more complicated, let me remind you what it looks like, it's this one, it's not enough to to take a solution, a plane wave with a P1 and a P2, and also add P2 and P1. You need to have additional momenta, which are not related to the original ones by permutations. So, because basically, if you try to solve these equations where the total momentum is the sum of either P1 and P2, your original momenta, or these new momenta, and at the same time the energy is the same, the two magnon energy, you find that there's an extra solution where these Ks are given by this equation as a function of the Ps. Now, this by itself seems to violate one of the criteria for integrability, in particular one by Sutherland, which is that one should not have diffractive scattering. So the set of initial momenta should be the same as the set of the final momenta. However, there's a bit of a loophole here, which we don't know if it's really going to work in our case. It definitely works in the two magnon case, but two magnons don't really indicate much about integrability. That's the idea of discrete diffractive scattering, which applies for some known non-integrable cases, for instance, the spin 1 XXX spin chain, where you can actually still have some element of solvability. You can solve, for instance, the 3 magnon problem by adding a finite amount of diffractive terms. In this case, we only have one extra diffractive term, which are these K momenta. Anyway, I'm going to skip through the solution. I just want to show that, okay, there is a bit of complexity in solving the model. And we have two solutions, which are given, everything is given as functions of these two equations here, which are deformations. So if kappa goes to 1, the ratios become 1, and these both become the standard XXX relations. But it's not so important. At least it's given the time. I just want to show that, okay, using the solution, you can write down a Bethe ansatz, and the Bethe ansatz can be expressed fully in terms of the original P momenta. There is some X function here, which depends on the K momenta, but the K momenta are functions of the P momenta through this arc cos that I wrote earlier. And by solving that, you can explicitly check that the Bethe ansatz matches the explicit diagonalization, at least for short chains that we looked at. Something similar happens in the XZ sector. You get the same dispersion relation, strangely enough. The ratio function is different, but the solution works in the same way. But as I alluded to earlier, the solution for 3 magnons is quite challenging, and it's a subject of ongoing work to try to understand how to take this already very complicated Bethe ansatz at 2 magnon level and promote it to a 3 magnon Bethe ansatz. So I don't have anything more to say about that today. What I want to do in the last maybe 6-7 minutes I have is to give an interpretation of this spin chain as a statistical or RSOS vertex or dynamical vertex model. So let me remind you, or just quickly summarize what RSOS or restricted solid-on-solid models are. These are lattice models where your Boltzmann weight, so you should think of a square lattice where this weight is one of the unit cells of the lattice, and the value of this cell that you need to put in, say, the partition function of your lattice is given by a Boltzmann weight, which depends, crucially, on these vertices, on some numbers, some integers, which are placed on the vertices, which are called heights. These types of models were introduced by Andrews, Baxter, and Forrester. And in the original model, which is actually linked to the XYZ chain, which was famously solved by Baxter in the 70s, they contain elliptic functions. You can see there are 6 different weights, and they are solved in terms of theta functions. And crucially, this is going to be important in a minute. The value for the weight depends on this parameter A. So it depends on the height. Okay. The other thing to notice here is that the heights in the original model are only allowed to differ by 1. So there is a condition on the neighborhood heights that A minus B has to be equal to 1. Okay. I'll come back to that in a second. These solutions, these weights satisfy the standard triangle relation. I'm still talking about the original ABF model. Pictorially, it looks something like this, for which you can recognize some version of the Yang-Baxter equation, of course, and this guarantees integrability of the model. Now, a powerful way of discussing more general kinds of RSOS models is by talking about adjacency diagrams. In the original so what that means is in the original ABF model, these heights can be any integer value. So that they take values along a real line. However, in a restricted RSOS model, then these heights are fixed to take values in an interval. And you can draw an incidence diagram, which actually Pasquier proves can be mapped to any AD Dinkin diagram. So any Dinkin diagram of an AD theory can actually be the incidence diagram for a RSOS model at criticality. There are generalizations of these, but the main one I want to focus on is the cyclic ISOS models, where the largest height is related to the lowest height in this way. So just to give two examples, this is an RSOS case. There are 3 heights for A3, and they're called 1, 2, 3. But for this A21, the affine SU3, if you wish, group, then you get, of course, the Dinkin diagram of A21, and which means that you can go up from height 3, but that takes you down to height 1. And Jimbo and collaborators showed that actually you can generalize this to not only the Dinkin diagram, but to actually all the dominant weights at level K of an affine algebra. And don't have time to explain this, but you'll see the picture. The last element is the dilute element. So you can make these models dilute by relaxing this condition, A minus B equals 1, to allow also A to be equal to B. So you can allow 0 as well here. That adds additional weights. For instance, you see here, this in the ABF was not allowed to be the same. It had to differ by 1. Now you're allowing also these extra weights. And the dilute notation comes, okay, I don't really have time to explain it carefully, but it comes because you can think of different weights as being on opposite sides of a domain wall. So this red line is a domain wall here. And the ABF model is just these 2 tiles. So it's dense in the sense that there's always a domain wall. But for the dilute models, you can have the same weights on different sides. And that's kind of dilute because the domain wall doesn't have to go through every vertex of the theory. The last element I want to very quickly discuss in the last maybe few minutes is that you can also convert these models to vertex models. So far I was talking about face models. They can be converted to vertex models graphically, basically by mapping these tiles to an R matrix. So this represents an R matrix, and this was discussed by Felder or introduced by Felder, and the main application for that was to elliptic quantum groups. The important thing for us is to note that this R matrix depends on this dynamical parameter, lambda, which is related to this D. And now remember that this D, the elements of the face actually depend on D. So this R matrix also depends on it. And that means that this cannot actually satisfy the usual Yang-Baxter equation. It has to satisfy a dynamical version of the Yang-Baxter equation, which looks like this. This may be not completely transparent, but maybe a graph will help. So this is the usual way that we write the Yang-Baxter equation, but now there's a dependence on lambda, which I denote like this. So this is the R matrix, each vertex is an R matrix, but the R matrix is different depending on what the value of lambda is. And every time you cross a line, your value of lambda is in principle different. And just to emphasize that this has also been used in these works by Junya Yagi, who also used this notation here. The application was also to quiver theories, but to the BPS sector and defects and not to planar integrability or spin chains, as I'm discussing now. Okay, so I can come now to the claim that I want to make, which is that by giving this very brief background, that we can map the whole SU3 sector, so both X, Y, and Z fields of this interpolating theory to a dilute CSOS model. The reason which dilute is because when you cross the Z field, this lambda parameter which tracks the gauge group is not changed, while it is changed if you cross the XY, so that makes it dilute. And it's also cyclic because if you cross 2 bifundamentals, you go back to the same gauge group. So lambda should be identified like this. This is the precise identification, although I must admit that we don't yet have the precise Boltzmann weights that make this really true. This is at this stage pictorial, and it's what we are trying to get. We've pointed out that there's this equivalence, and we're trying to find the specific Boltzmann weights, regardless of whether they satisfy the star triangle relation that realize this. So maybe just to quickly come back to the adjacency diagrams, in this way of thinking of RSOS, you can think of the n=4 theory, so XXX, as a trivial CSOS model where it's not dynamical. It's the same parameter everywhere because every time nothing happens if everything is the adjoint, nothing happens when you cross lambda. But in our Z2 case, in the orbifold case, every time you cross an X field, lambda changes. That's why you have red and blue nodes. And this is actually mappable. This graph, which is the adjacency diagram of the statistical model, is actually exactly the same. It's the dual graph to the bipartite graph that I started with for the gauge theory, for the quiver theory. This generalizes also to any other AD orbifold quite kind of simply. So for the Z3 case, you would have now 3 values of lambda, which would be different, which correspond to the 3 gauge groups. So then the goal, again, is to find an RSOS model describing this adjacency diagram. Okay, I'm done. So maybe I can just quickly summarize that we looked at spin chains in the Z2 quiver theory. And depending on the sector we chose, these were alternating spin chains or dilute spin chains. And the dispersion relation was elliptic. We found the 2 Magnon wave function was unusual in the sense that there were additional momenta you needed to add to solve the problem, the eigenvalue problem. And we found some intriguing links. At this stage, I would not say it's a proof, it's a link to RSOS models and the dynamical vertex models. There's many things I did not cover in this talk, which are in the paper. In particular, the link to elliptic quantum groups, we tried to make it a bit more precise. Also, we talked about quasi-Hopf symmetries. Again, there is no time to really go through that right now. But if there are questions, I can happily answer. And just to give you a bit of outlook, obviously the 3 Magnon problem is one of the main things on our mind, which will impact on the question of integrability and solvability. The signs are definitely not that it's integrable, but there may be some element of solvability might still be there. And we are also interested in finding the specific weights which realize its adjacency graph. I did not explain carefully what they need to imply, but it's quite likely that there will need to be elliptic weights depending on some theta functions in order to have the right periodicities required for this adjacency graph. And there's many other possible extensions. For instance, one can go to bigger sectors. We can try to understand the deformation of PHE 2,2/4, which is the full superconformal algebra of n=4. What happens to it when, first of all, you orbifold and then you deform? So is there some kind of quantum group way, elliptic quantum group way of understanding that? That's a very interesting current question. And you can also go to more general quivers. And maybe let me end with the question of whether this link that we seem to be uncovering between quiver theories and RSOS models is kind of more general, maybe more general than the n=2 theories we're looking at. And is it somehow an extension, perhaps non-integrable, but it doesn't point to a much more wider relation between gauge theory and 2-dimensional statistical models. Okay, that's all I had to say, and thanks a lot for your attention.
Let's see if there are any questions from the audience. I see none.
I see Carlos has raised his hand.
Carlos has a question.
Thank you. Costa, can you hear me?
Yep.
Costa, let me make one statement and tell me if it's correct. It's from the ignorance, so apologies in advance. When you make this Zn, right, and I saw in your drawings that you have the possibility of different gauge couplings, for example, there, right, the lambda, lambda 2, lambda 1. So yes. Suppose that all the lambdas are the same, or in the other drawing, lambda, lambda prime. Is that integrable? Is that correct?
Yes, yes. That would be what I would call the orbifold point.
Good,
so that's when you just take the orbifold and you do nothing else. You don't marginally deform.
Good.
Yeah, that is definitely integrable. Good. As shown by Bison Royban.
Exactly. So what I was not reminding is I remember Bison and Radu showing it for the 2 nodes, say the Z2, but I didn't remember that it was shown for any.
No, actually, in their paper, I mean, they were a bit compact in their paper, but actually they effectively showed it for Zn.
Okay, good.
So any cyclic orbifold that you want to do, I think it's that part is quite clear. But there have also been extensions to more general non-abelian orbifolds.
Okay, and another in this sense, in this line, suppose that you consider, instead of these identifications of n equals 4, say linear quivers, right? Like the ones I was discussing before. And is it the case that every time you have a flavor group, this will spoil the integrability?
No, actually, in the original work by Rastelli and Pomoni and Gade, right? That was one of the points that they were interested in. They actually added a flavor group by taking this and taking one of the gauge couplings to 0, right? And that made it global. And funnily enough, they found that in that limit, like if you just write down the S matrices for the general interpolating case and then just by hand take that limit of one of the couplings to 0, that satisfied the Yang-Baxter equation.
I see.
Now, the problem is that you don't really have a spin chain in those cases. I mean, obviously, you can try to think of a linear quiver where you have just an open spin chain, right? Maybe that's what you're asking more specifically.
Exactly.
Yeah. Okay, we haven't looked at that. I think there's different things that can happen when you have open spin chains, and some of them are integrable, some of them are not, as you know, depending on different orientations of the flavors and the boundary Yang-Baxter equation if it's satisfied. So we haven't looked at that, but in the specific case that Rastelli and Pomoni and Gade looked at, the spin chain actually breaks. It becomes like it gets dimerized.
I see.
Because it's already an alternating chain, and if you make one of the groups global, you get just somehow dimers. And there, it's a little bit difficult to talk about integrability with the usual, planar integrability language that we are familiar with. But if you're just asking add a flavor group at the end of the quiver or something like that, and then try to have an open chain, anything is possible. It could be integrable. But of course, we're still working on understanding if there's any integrability for just the purely bifundamental and adjoint sectors. If we understand that, then obviously
you will move into
the next step.
Okay. Thanks very much, Costa.
Thank you, Carlos.
Okay, let's thank the speaker once more. We go for coffee and reconvene at 6.